Okay, this is a about Fets. Most of the stuff on this slide has to be memorized. I don't know what else to tell you. So you need to know, each Fet has three connections. One is the gate, so the gate is on this one here, and the gate on this one is here. There's two kinds of Fets. There's an N Fet and a P Fet. The N Fet is the one that's over here, and this is the P Fet. On an exam, I might draw you a picture and ask you which one's which. You have to figure out some way on your own of memorizing it. It's up to you. What I do is I look at this little arrow. Looks like an arrow anyway. I look at that guy and I say he's pointing in, so he's the N type. This guy's not pointing in, so he's not the N type right here. But however you want to remember it, that's you just have to remember it. The gate I pointed out. The source, the way I remember it, is the source is the line that connects up to all of the arrows in the middle. So, for example, here is connected up to here, so this is the source, and this one over here, this little arrow connects up to here, and this is the source. But again, just remember it. You just have to remember it. Don't think it's the N, it's always on the bottom, and on the P, it's always on the top, because I could just draw these, flipped over 180 degrees or something and fool you. So you have to remember which one's which. And then the one that's left over, right? So this is the gate. This is the gate G sources. The one that's left over is called the drain. So this guy up here is the drain, and this one down here is the drain. All right, so that's that one. The current, these are switches. That's the way we use them anyway. I mean, other people could use them for whatever they want, but mechanical engineers, we typically use them as switches. And the voltage on the gate is what turns the switch on and off. And when the switch is on or off, the current flows between the source and the drain. Now, the way the current flows is opposite this little arrow here. So, for example, you can think of it as maybe a blockage or whatever. But when the gate is, or when the switch is on, current will flow opposite this little triangle that I've circled here, and over here it flows opposite this one. So when this switch is on, current is going to flow from the drain to the source. When it's off, it turns off, and you don't have maybe a little bit, but you don't have much current at all that flows through there. On the P type over here on the right hand side, when it is on, it flows opposite this little arrow, and so here it's going to flow from source to drain. Current always flows, well, conventional current always goes from the positive voltage to the negative voltage. So over here you'd want to put a higher voltage on your source than on your drain, so that when you turn it on, the current will flow in the correct direction. On the N type on the left hand side, you want to put a positive voltage up here on your drain, so that when you turn the gate on, or when you turn the switch on, you'll get current flowing in the correct direction. So you need to know that, so you know which way to wire it up when you want to try to use it. Typically no current goes in or out of the gate as long as you got it hooked up properly. So there's very little, it's like 10 to the minus 9 or something, really small current that flows in or out of this gate. Kind of makes it look like there's a gap in between here, and so you can think of it that way if you want to, or whatever, but just remember there's no current that'll go in or out of the gate. The way you turn it on or off is you make the gate voltage, which you think of voltage as pressure if you want, you make the gate voltage higher or lower than the source. So you have to know where the source is. So over here on the left hand side, the source is on the bottom. And what you want to do in this case is you want to make the gate voltage higher. So I'll draw a little up arrow right here. You want the gate voltage to be higher than the source voltage, or the pressure, or whatever you want to call it, to turn it on. The way I remember this, you have to remember it, the way I remember it is I look at this little arrow right here and I pretend like what I want to do is force current backwards across this arrow. In order to force current, you want a high voltage here on the gate. So I want a high voltage on the gate, so it will try to push the current. Nothing goes through there, but tries to put, that's just the way I remember it, tries to push the current across this little arrow. So this voltage here has to be higher than the source. Okay, over here on this side, same thing. I want to pull the current across this arrow, backwards across this arrow. So what do I want? I want this to be high, and I want this one over here to be low, so that if a low pressure will tend to pull the high pressure backwards across that arrow. You've got to memorize it. That's just the way they work. Don't ask me why. Don't ask me how. I don't know, but that's the way they function. Right? So that's how you do it. Okay, so in this particular case, you have a FET, which is a switch. You have a couple of resistors, and you have a controller that's over here. This is what's trying to control it. Typically, this thing over here, SW1, will be a computer, and the computer is going to apply a voltage, either high voltage or low voltage, to the FET. And so your computer then turns on your load. The reason you do that is because your computer typically does not have enough power, enough current to drive a motor. Right? And so we're mechanical engineers. We like to drive big heavy motors, drive a car, whatever it is. And so you just don't have enough power from your computer to turn things on and off. So what you do is you have your computer over here, and it turns on and off your FET, which then drives your load. Okay, so in a case like this, shown a picture here. There's two resistances. Your load doesn't have to be a resistance. I'm just trying to make it simple. The question is to find the load. Well, the load always goes between the or goes in line with the source and drain. So you got to find out where your source and drain is. Well, in this case, here's the gate, here's the source, and here's the drain. So this resistance right here is the one that goes into the drain, through the source, and over to ground. So this guy right here is your load. Why is it up there? I don't know. It's just the way I drew it. Maybe you want it down here, whatever. But this guy right here is the load. That's the thing you're trying to turn on and off. All right, so that's the load. Find the control. The control is back over here, because this is what controls the FET and turns the FET on and off. Right? Pretty simple. Low side or high side switch. Well, what you do is you look for the load. You found it. Here it is. When the load is on, typically there's a current. I mean, that's what you're trying to do. You're trying to turn it on and run current through the thing so that it does something. So when the load is on, you will have current that goes through the load. Current will go from the high voltage side to the low voltage side. So you'll focus yourself on the resistor and ask yourself, which way is current flowing? Well, if it's turned on, obviously current is going from the high voltage down to the low voltage, so it's going in that direction. Okay? One of the sides, either here or here, has the higher voltage when it's turned on. Well, the back side of a resistor right here, the tail side of the current, is always the higher side of the resistance. So this one right here is the higher voltage side than this one right here. Okay? So this is the big blue dot. That's the high side of the load. This, with the X, is the lower voltage side of the load when it's turned on, because the current is going from top to bottom, right? Because it's grounded here, it's high voltage here, so it's going to go from the top to the bottom. Don't always assume it's top to bottom. Look for where the voltages are and where the ground is. Because if I rotate the picture, I'll fool you. Okay, so anyway, the X is the low voltage side of the load. Where is the switch? The switch is right here. This is the switch. So is the switch on the X side of the load, or is it on the dot side of the load? It's obviously on the X side of the load. The X side is the low pressure side of the load. This is a low side switch because the switch is on the low side of the load. So it's a low side switch. The purpose of this R here, R1, that is the load. That's your motor, that's your light bulb, that's whatever it is that you're trying to control. That is, why that is there. The purpose of this is for noise, because if the switch were to open, if the switch over here, SW1, opens up and there's no connection there, then this wire right here that I'm going to kind of just draw a zagged line on it, so that wire right there, there's no connection on it. And if there's no connection on that, who knows what the voltage does? If there's an electrical storm or some sort of a electromagnetic wave coming through the factory or whatever, you might fluctuate this voltage on this wire because nothing is holding it high, nothing's holding it low. And what could happen is you could end up driving the voltage noise, it could drive this voltage here up because nothing is holding it down or up or whichever. And so what could happen is your FET could just accidentally turn on when you have an electrical storm. So what's the purpose of R3? Well, the purpose of R3 is that if switch 1 is not connected, if it's off, opened up, then something is holding this wire right here that I'm squiggling in, something is holding that voltage at 0. And it's that resistor R3. And so what happens is when there's no connection on SW1, this squiggly line, this line right here, is being held to 0 volts, and that means that that FET will stay off. So it won't just automatically, accidentally turn on because of an electrical storm. That is the purpose of this thing. Okay, so how do you approximate the currents and the voltages? All right. All right, so let me kind of erase everything and do it again. Okay, so here we go. All right, so how do you approximate this these voltages? Okay. All right, when this guy here is tied to ground, so all of these voltages here are approximately 0. Well, they're not approximately. They're tied to ground. They're 0. Okay. So when the switch is closed, like it is now, what's going to happen is you have 6 volts right here, which is going to come across here, and so you're going to have approximately 6 volts, or you're going to have 6 volts right there. So that's what this line is going to do. Okay, and so now if you have 6 volts back here on the back side of this guy, you can approximate the amount of current that goes through here, because it'll be tail voltage 6 minus head voltage 0 equals the resistance, and my eyes are, I think that's 1150, resistance 1150 times the current that goes through there. So you can solve for the current that goes through this guy right here. So you can solve for that current approximately, right? Okay, now because you have a high voltage here on the gate compared to the source, which is right here, you have a higher voltage. You're trying to, it's like, the way I remember it is you're trying to force current across that arrow. So in other words, you've turned on this switch. If the switch is on, the voltage here is going to be approximately the voltage here, which happens to be 0 in this case, right? Now if I put a battery in here and this was 3 volts, well then this would be approximately, if whatever this one is, right, 3 volts, 4 volts, whatever, approximately the same thing that's going to be up here, as long as the FET is on. So if the voltage here is approximately 0, the voltage on the back side of this guy is 12, then you can count, or you can calculate this current here, we'll call it I1, because the tail voltage 12 minus the head voltage, which is when the FET's on, is approximately 0, is equal to R, which is 1, times the current, I1. So the current is approximately 12. Okay. Now if you look, this is a simulation. If you look at this guy right here, here is the simulation value, and it's pretty close to 12. It's 11.8. Why is that? Well, because the FET's not perfect. The FET has a little bit of a resistance to it, so when it's turned on all the way, it won't be exactly, it's not a perfect switch. And how much voltage is across it? This much right here. Okay? So, but what I would be expecting you to do is to say, well, you know, approximately when the FET is on, this is going to be approximately the same voltage as what's on the bottom, which is 0. The approximate, so this is approximately 0. The current is approximately 12, and it won't be exact, but close enough for what most of the work that mechanicals will do. Now what I'm going to do is show you when it's off, and also how to read the data sheet, which is this guy right here, to try to make predictions on that. So that's what's next. I'm going to pause for a minute. Okay, so I've shown you how to approximate this. Now let me show you the data sheet for this particular FET. I think I've got it up here. Right. Well, here we go. Okay, so here's the data sheet. This is the first page of the data sheet. And there's a couple of things that it tells you, like for example right here, that gives you the maximum current that can go through here. This FETs kind of look like resistors when they're all the way on. I'll show you in a little bit, but they're not resistors. You can't use the formulas for resistors and whatnot, but they kind of look like a resistor when they are completely turned on. And what they're telling you here is that the FET looks kind of like an 11 milliohm resistor. Okay, so let me just come over here and draw a little picture of what we had before. We had a 12 volts up here, and it went through a 1 ohm resistor, and that was the load. And then it went through the FET. I'll draw a little circle here, and when the FET is on, it's kind of like a resistor. And then it went to ground. And so the resistance of this guy is 0.011 ohms. Okay, so what I'd like to know is what's this current right here? What should be this, what's this current? Well, the resistance, these are in series, and so the resistance is 1.011. So the current is tail voltage 12 minus the head voltage 0, right? So the voltage back here, 12 minus this voltage 0, equals the resistance, which is 1.011 times I. If you solve for I, it's not hard to do. I think I did that on my calculator. Let me pull it up here real quick. It is 11.87. 11.87. So what's the voltage right here? Well, the voltage at that point ought to be equal to the current, 11.87, times the resistance of the FET. And remember, it's just an approximation. It's not really a resistance. So 0.011. So if you take 11.87, you multiply by 0.001, so 11.87 times 0.011, you get 0.13. 0.13. Okay, let's look back at our simulation. See if I can get back there to it, or to our slide rather. So here we go. This voltage right here, see it right there? I was predicting 0.13. The simulation shows it to be 0.14. I'd say that's pretty good. The current that I had was 11.87, I think it was. And look at what the simulation is showing, 11.8. So you can see once you have a data sheet, if you really need to know exactly how much that is, it's not hard to do the calculation. On an exam, what am I expecting? I'm expecting that you'll be able to approximate these values, which I've shown you in the blue of how to approximate it. Okay. Let me pause for a minute. Okay. So what I want to do is show, I'm going to pull up the simulator and show what happens when the switch is off, and we'll then look and see if we can make predictions of what we would have expected to see on that one. So here's the simulator. See if I can zoom in. So I want you to focus on this one right here. There we go. I think that's, yeah. So this is the one that I had before. And now the switch is open right here. So whoop, I guess I can't write on this one. But right in here, maybe I can point to it. Right in here, because switch 1 is open, the voltage at this point right here on this wire is going to be 0, right? Because of this resistance. No current can come in or go out of this gate, and there's no connection here, so there's no current in this wire. If there's no current in the wire, this resistor can't have a voltage across it. So the voltage that's here at this point would have to be 0, right? So because the pressure here, the voltage here, is not larger than it is at the source, the FET's going to be off. So this thing is off. So if it's off, what would you expect? You would expect very little current to come through the drain to source. And if very little current comes through there, then you would expect the voltage on the bottom of R1 to be approximately the same as it is at the top. So let's run it and see what happens. Okay, so here it's running, and you can see right here, this little arrow is saying the voltage at this point is 12 volts, as you would have expected. The current that is coming through this thing, you see this little circle with an arrow in it? Okay, so it's telling you positive current is going down this way. And notice how much it is. It's 1.2 times 10 to the minus 5. Well, for crying out loud, that's 0. And again, how much current is going into the gate? 10 to the minus 16. Nothing. Right? So what's this voltage here? Well, this voltage here is 10 to the minus 8. It's 0 essentially. Okay? So that's probably what you expected to see. All right. So the next thing is to take a look at the data sheet. Let's see if I can find it. Here we go. Here's the data sheet. Let me make it a little bit bigger. I've shown you the first page, which was right here, and we made some calculations. One of the other things that's important for you to look for on FETs is the threshold voltage, which is right here. Let's see if I can write on this one. Threshold voltage right there. VGS threshold. So whenever they give you subscripts GS, that is the voltage where you know how to measure voltage. You take a voltmeter, it's got a red wire, it's got a black wire. You take the red wire and put it on the first subscript, you take the black wire and put it on the second subscript. So this is the red lead on the gate, black lead on the source, and its threshold is anywhere from 2 up to a maximum of 4. What that is it's kind of like a faucet. These FETs are like maybe water flowing through a faucet, and you can open the faucet just a little bit and it just dribbles. That's the threshold voltage. So at a voltage of a maximum of 4, the FET is dribbling, if you want to think of it like that, right? So what I'm going to do is go back and set the voltage on the gate to be the threshold voltage. So I'm going to go back to the simulation. Yeah, here it is. I'm going to go back to the simulation, and unfortunately I got to zoom in again, but okay, whatever. Let's stop the simulation from running. Over here, let me zoom in on this guy. It was a 6. I'm going to make it a 4, which is the maximum threshold. Okay, so that's a 4 volts there. And now what I'm going to do is I'm going to run it, and we're going to see what the FET does. So I'm running. Let's close the switch. Click. So the switch is now closed. The voltage that's here, you can see, is SW1NO. The voltage there is 3.99997, basically 4. But look over here. I'm going to zoom in on the FET, and let's see what the FET's doing. All right. So what's the voltage that's on the bottom of R1? It's about 10.7. Right? Before, when we hit the FET with 6 volts, it was definitely on, and that voltage was pretty close to being 0. Now it's cracked on just a little bit, and the voltage there is 10. Look at the current. The current that's flowing is 1.27 amps. Right? So basically, if you hit the threshold voltage, it's not off, it's not all the way on, it's partially on. One of the things that I would expect you to be able to do on an exam is, if you're given information like this, if you're given this picture, I would expect you to be able to determine how much electrical energy is being turned into heat from in the FET. And the way you would do that is you would say, add up the amount of energy going in, subtract out the amount of energy leaving, and that's the amount of energy approximately that gets turned into heat. So in this case, how much current's going in, and unfortunately I can't draw on this guy, but the current that's going in is 1.27. The voltage at this lead is 10.72. Let's see if I can pull up my scroll. Okay, so no, let's see. Here we go. We'll put them side by side. So all right, so over here I'm just going to we'll put it up here in the margin. Okay, so the power going into the FET at the drain is a voltage of 10.7. The current that's going in there is 1.27 amps. That's going in, so I'm going to say that's positive power going in. The power that goes into the gate is practically nothing because there's very little current. The power that comes out is coming out and going into the ground device. The voltage at that terminal is 0 because it's ground. The current is 1.27 because whatever goes into the FET has to come out of the FET, 1.27. So that equals 10.7 times 1.27. Okay, 10.7 times 1.27 is approximately 13.5. 13.5. So what's happening is, when you're driving this thing at the threshold voltage, according to the data sheet at the threshold voltage, you're dissipating 13.5 watts of energy in that FET. That thing is going to get hot. So basically you don't want to get it, you don't want to turn it on at its threshold voltage. Okay, I'm going to pause now before I go to the next phase. Okay, I'm looking for my data sheet again. Here's my data sheet. Okay, so let me so there was the threshold voltage. So let me show you some plots down here. You want to make sure, you know, as a mechanical engineer, basically you just want to either turn this thing all the way on or turn it all the way off. But the threshold gives you a little bit of an idea of how much voltage you're going to need to do that. The other graph that I like to look at is this one right here. This comes from the data sheet. So when you buy your FET, it'll, you know, the manufacturer, I mean, if you buy it from a retail store, they probably won't, but if you buy it from a supply house or something that deals in this stuff, they'll always give you a web page that points to the data sheet. So here's a data sheet. One of the things to watch out for as a mechanical engineer is when we plot things like this. We plot things like this, like pump curves, motor curves, things of that sort. we typically plot the flow along the horizontal axis and the effort, torque, force, etc. along the vertical. So for example, if this was a piping diagram, you would have volume flow rate along the horizontal and you would have pressure along the vertical. For some reason, electrical circuits tend to reverse those, and so you have your flow along the vertical and your effort variable along the horizontal. So you just have to be aware of that. They're kind of backwards from what we're used to. Okay, so on this guy, which I think I can do, this is your voltage between the drain and the source. And if you remember the example that we had, on the high side of the load you had 12 volts, and on the other side you had ground. So the source voltage on our application was 0, and then the drain was whatever current came through across that thing. So anyway, that's the voltage that we're looking at across the FET. And the reason that they're often given as a resistance is if you look at this area right in here, unfortunately it's going to come in black, but if you look in here, right in here, see how those lines, especially the ones up towards the top, they're basically straight, right? And because they're straight, it acts like a resistor, right? Because that's what the voltage to current relationship on a resistor is also straight, right? Voltage equals IR. And so that's why they quote it as, and of course this is a log-log plot, but anyway, so it's that straight business that they're emphasizing here. I'm plugging in, trying to plug in. Okay, but anyway, each of these curves, like this one here, 4.5, that is the drain to source, let's see, excuse me, that is the gate to source voltage is 4.5. So this is just a little bit above, half a volt above what they claim is the threshold voltage. And you can see that what happens is it won't pass very much current because the current is over here on this axis, right? So the maximum current it's going to flow is not that much, but you are going to get a rather large voltage, and that's what we saw when we were driving it at the threshold. So if that's not what you want, which is typically not what you want, right? You want the switch to be on. You don't want a large voltage drop across your switch. Then what you want is you want to be up in here, right up in here in this range, so that you can get a lot of current, right? So for example, you have a large current over here, and the amount of voltage that drops across your switch is not very much at all, right? So that's what you would use this curve for, is to try to identify how much of the voltage right here, voltage to source, that you really need for this. And so what they're saying is the very top one, you have 15 volts. Threshold is 4. If you apply 15, you're going to be up here at the top end of that spectrum. So that's basically how then when you buy this thing, you know what kind of voltages you have available to you, and so you'd be looking for something that because normally you don't want to burn up your power in the switch. You'd be looking to see if you can get the voltage that you need to drive this particular FET. So that's what this diagram here is for. So let's go back to the PowerPoint.
Verizon Wireless.
Okay, we're back here at the PowerPoint, and what I've shown is how to approximate the voltages and the currents when you don't have the data sheet. I've shown, if you have the data sheet, how you can find more realistic values for what's going on in here. The numbers that are shown here, by the way, are coming from the simulation. I also showed you the threshold voltage and what happens to the FET when you drive it at the threshold voltage. It doesn't turn on all the way, doesn't turn off all the way. and you will, depending on the circumstances, you could be burning up a lot of electrical energy in the FET, which means it's going to get hot. Now the next thing is, what happens if you try to use a FET and you saw in the data sheet that this was a 85 amp FET. What happens if you try to force more than 85 amps through that? So what I'm going to do is change the value of R1 and make it smaller and smaller and smaller, so that when the FET is on, there will be more and more current that is trying to go through the resistor, and we'll see what the FET does. So that's what I'm going to do next. And so let me see if I can find my there we go, there's my simulation. And so let's see if I can zoom in here. We'll zoom in. I'm going to change this resistance, and right now it's about 12 volts across there, so I want it to go to, let's say, 100 amps. So if I have 12 volts, I want 100 amps, then I want a resistance of 0.1. Is that right? V equals IR. Divide by that. Yep, about 0.1. So what I'm going to do is I'm going to change this resistance and make him a 0.1. Okay. So if it was completely on, I should be getting 12 minus 0. 12 divided by R divided by 0.1. So 12 divided by 0.1 is 120. So I should be getting about 120 amps through here when I turn him on. Okay, so here we go. We're going to do this, and let's see if I can get him to zoom in pretty good. All right, switch is on. We'll do a simulation. Bang. So now here are the values. Oh, I'm sorry. I should have. That was at the threshold voltage. Let me make this guy up at the 6 volts, like it was before. 6 volts. Boom. Okay. So now run the simulation. 6 volts on the gate. So he's, I guess, all the way on. The voltage now that you can see, it's 1.78. So there's a voltage drop that's across this. I'm running a current of 102. So I would have predicted, if this was a perfect switch, that the voltage labeled R1 parentheses 1, you would have expected that to be small, which it's not. It's 1.78. And the current, you would have expected 120, and it's lower than that. It's 102. You can calculate the energy that's being dissipated by the FET, which is going to be 1.78 times 102, which is a lot of watts going through that. So what we'll next do is say, well, suppose I drive the gate a little harder. So let me stop that. Let's make this a large number. Not sure what the maximum is. I haven't looked at the data sheet. I'm going to make it 12 volts. We'll see what happens now. And run the simulation again. And again, this is 12 volts on the gate, so it should be smacked it well. But still, your voltage is 0.97, right? Your current is 110. It's getting a little closer. It's not a perfect switch. You're losing about a volt drop across that. The amount of power that's being dissipated is 0.97. That's close to 1. Let's call it 1. 1 times 110, you're burning up 110 watts in this FET. So you better get it cool, or else you're in deep trouble. If you look at the data sheet, if I can figure out how to, here it is. I think this is the data sheet. So if you look at the data sheet, right here, the gate to source is about 12 volts. So we're on the, not the top one, but the middle one. So we're on this this edge right. Let's see if I can draw on this guy. Oh, I lost my pen. We're on the second row down. The voltage drop across this guy is about 1 volt, which is about right there, and the current that we're running is about 100 and something amps, which is right there. So it's basically operating right there where you, oh, here's the pin. So we're on this row right here, because the top one is 15. This one right here is 10. We're somewhere between 10 and 15. And if you notice, the voltage across the from the drain to the source is approximately 1 from the simulation. So we're right about there, and the current that we're pushing through that thing is a little more than 100 amps. So the graph is predicting what you would have expected. But anyway, the point is, if you're running 85 amps through this thing, you're going to have, according to this chart, you're going to have a significant voltage drop across it, and a large current. And so that's going to be a lot of power. And what you're going to have to do is keep that FET cool. So, how much can you run through this? Well, it gives you maximum ratings up here. So let's see, the maximum rating for this, 85 amps. You see I've got it circled there. So the maximum rating is 85. Here, ID, right here, this is what they're, right, ID, the current into the drain, maximum 85 amps. If you're running at 10 volts, let's see, yeah, okay, the TC, that's the temperature. So if you're cool, then you can run 85. If you're not, if you're up at 100 degrees centigrade, you can only do 60. So gate to source, okay, that's another one that you might kind of watch when you're building one of these things. It's only 20, so the gate to the source can only be 20 volts. In our case, the most we had was 12, not a big deal. They give you a thermal resistance, so once you've had heat transfer, you say, well, I need to know if I can get that power out of it. That's good. What else do you need to probably know? That's probably enough. Continuous. Well, we've covered that. Continuous current, 85 amps. So I think that kind of shows it. On an exam, what am I expecting you to do? Well, what I'm expecting on an exam is basically these kinds of things that are here on this chart. Find the load, find the control, whether it's a high or a low side. Why are the resistors where they are, and what difference does it make? And then to be able to approximate these values. That's what I expect on an exam. If you're going to use one and build one, then you want to get the data sheet. You want to know what the threshold voltage is. You know that you better be above the threshold voltage when you hit it with the gate. You should not be near the rated current unless you've got it cooled. Those are the things that you need to know in order to use these things. Exams, I expect you to be able to kind of approximate what these things ought to be. That should do it. I hope that helps you.